Hello everyone. I am Din Shabbir Chaudhary, faculty in Arihant Junior College of Arts, Commerce and Science, Camp, Pune. In previous video, we see differentiation. Now today, I am going to explain you applications of derivatives. Introduction. In the previous chapter, we have studied the derivatives of various functions such as composite functions, inverse, trigonometric functions, logarithmic functions, etc. And also the relation between derivative and slope of the tangent. In this chapter, we are going to study various applications of differentiation such as application to first geometry, second rate measure, third approximations, fourth Rolle's theorem and Lagrange's mean value theorem, fifth increasing and decreasing functions, and sixth maxima and minima. So first we see application of derivative in geometry. Let y equal to f of x be a continuous function of x representing a curve in xy plane and p of x1, y1 be any point on the curve. Then dy by dx equal to f dash of x at point x1, y1 represents slope also called gradient of the tangent to the curve at p of x1, y1. The normal is perpendicular to the tangent, hence the slope of the normal at P will be the negative of reciprocal of the slope of tangent at P. Let M and M dash be the slopes of tangent and normal respectively. Then m equals to dy by dx at point x1, y1 and m dash equals to minus 1 upon dy by dx at point x1, y1 if dy by dx at point x1, y1 not equals to 0. Equation of tangent at p of x1, y1 is given by y minus y1 equals to m into x minus x1. That is y minus y1 equals to dy by dx into x minus x1, and equation of normal at p of x1 y1 is given by y minus y1 equals to m dash into x minus x1, where m dash equals to minus 1 upon dy by dx at point x1 y1. For example, given that y equals to 2x cube minus x square plus 2, differentiate with respect to x, dy by dx equal to derivative of 2x cube minus x square plus 2, which is equal to 6x square minus 2x. Slope of tangent at 1 by 2 comma 2 is equals to m equals to 6 into half square minus 2 into half. Therefore, m equals to half. Slope of normal at half comma 2 equals to m dash equals to minus 2. Equation of tangent is given by y minus 2 equals to half into x minus half, which implies 2y minus 4 equals to 2x minus 1 divided by 2. 4y minus 8 equals to 2x minus 1, which implies 2x minus 4y plus 7 equal to 0. Equation of normal is given by y minus 2 equals to minus 2 into x minus 1 upon 2, which implies y minus 2 equals to minus 2x plus 1. Hence, 2x plus y minus 3 equals to 0 is the solution. Second example, given that x cube plus 2x square y minus 9xy equal to 0. Now differentiate this equation with respect to x. We get 3x square plus 2 into x square into derivative of y plus y into derivative of x square minus 9 into x into derivative of y plus y into derivative of x equal to 0. 3x square plus 2x square dy by dx plus 4xy minus 9x into dy by dx minus 9y equal to 0. Now take dy by dx common. Therefore, 2x square minus 9x into dy by dx equal to 9y minus 4xy minus 3x square. Therefore, dy by dx equal to 9y minus 4xy minus 3x square divided by 2x square minus 9x. Slope of tangent at point 2, 1 equals to m equals to 9 into 1 minus 4 into 2 into 1 minus 3 into 4 divided by 2 into 4 minus 9 into 1. After solving, we get m equals to 11. Therefore, slope of normal at point 2, 1 equals to m dash equals to minus 1 upon 11. Equation of tangent is given by y minus 1 equals to 11 into x minus 2, which implies 11x minus y minus 21 equals to 0. Equation of normal is given by y minus 1 equals to minus 1 upon 11 into x minus 2, which implies 11y minus 11 equals to minus x plus 2. This equation also can be written as x plus 11y minus 13 equals to 0. Now, next topic is derivative as a rate measure. If y equal to f of x is the given function, then a change in x from x1 to x2 is generally denoted by delta x equals to x2 minus x1, and the corresponding change in y is denoted by delta y, which is equal to f of x2 minus f of x1. The difference quotient delta y upon delta x equal to f of x2 minus f of x1 divided by x2 minus x1 is called the average rate of change with respect to x. This can also be interpreted geometrically as the slope of the second line joining the points p of x1, f of x1 and q of x2, f of x2 on the graph of function y equal to f of x. Consider the average rate of change over smaller and smaller intervals by letting x2 to approach x1 and therefore letting delta x to approach 0. The limit of these average rate of change is called the instantaneous rate of change of y with respect to x at x equals to x1, which is interpreted as the slope of the tangent to the curve y equal to f of x at point p x1, f of x1. Therefore, instantaneous rate of change is given by limit delta x tends to 0 delta y upon delta x equals to limit x2 tends to x1 f of x2 minus f of x1 divided by x2 minus x1. We recognize this limit as being the derivative of f of x at x equals to x1, that is f dash x1. We know that one interpretation of the derivative f dash of a is the instantaneous rate of change of y equal to f of x with respect to x when x equals to a. The other interpretation is f of x at f dash a is the slope of tangent to y equals to f of x at point a comma f of a. One example is there: a stone is dropped into a quiet lake and waves in the form of circles are generated. Radius of the circular wave increases at the rate of 5 cm per second at the instant when the radius of the circular wave is 8 cm. How fast the area enclosed is increasing. Solution: let r be the radius and a be the area of the circular wave. Therefore, a equals to pi into r square. Differentiate with respect to t. d of a upon dt equals to pi into derivative of r square. dA upon dt equals to 2 pi r into dr upon dt. This is equation 1. Given that dr upon dt equals to 5 cm per second. Thus, when r equals to 8 cm, from 1 we get dA upon dt equals to 2 pi 8 into 5, which is equal to 80 pi. Hence, when the radius of the circular wave is 8 cm, the area of the circular wave is increasing at the rate of 80 pi centimeter square per second. Second example, the volume of the spherical ball is increasing at the rate of 4 pi cc per second. Find the rate at which the radius and the surface area are changing when the volume is 288 pi cc. Solution: let r be the radius, s be the surface area, and v be the volume of the spherical ball. We know the formula for v equals to 4 upon 3 pi r cube. Now differentiate with respect to t, we get dv upon dt equals to 4 pi upon 3 into derivative of r cube, and derivative of r cube is 3 in r square into dr upon dt. After solving, we get dr upon dt equals to 1 upon r square. This is equation 2. When volume is 288 pi cc, that is 4 upon 3 pi r cube, which is equal to 288 pi. We get r cube equals to 216, that is r equals to 6. From 2 we get dr upon dt equals to 1 upon 36. So the radius of the spherical ball is increasing at the rate of 1 upon 36 cc per second. Now s equals to 4 pi r square. Differentiate with respect to t, we get ds upon dt equals to 4 pi into derivative of r square, and derivative of r square is 2r into dr upon dt. After solving, we get 8 pi r into dr upon dt. So, when r equals to 6 centimeter, ds upon dt equals to 8 pi into 6 into 1 upon 36 equals to 4 pi upon 3. Hence, surface area is increasing at the rate of 4 pi upon 3 cm square per second. Thank you everyone for watching my video. Thank you.